see how important is this ledge deformation, we can do our simulation with 200 Newton half force, not 100 half force, but 200 Newton. Then I have really big deformation, yes? And then we can see difference between with ledge deflection on and without. So, if I do my simulation with ledge deflection on, and with ledge deflection on now with 200 Newton, then we see what's happened. Okay, we are watching force of against always. We see program tried, I repeat always, program yes, here program need more these steps, do you see? And didn't find solution, right? It means program tried to find it not with 100 but with 50 maybe. Yeah? We will see these pictures always, and we see what's happening. Yes, program tried to calculate 0.8 seconds, but it's difficult. Yes, 0.8 multiplied with 200 Newton, so much Newton we are trying to calculate. But it's difficult to receive red point. Red point means program tried less force to calculate. Yes. So then we see green. It means program found solution trying to make more time steps. So, for example, I can check also time. Yes, time. What's happened? How program works? Program tried to calculate 0.2, no problem. Then 0.84. It was red. The program goes down, and then grow up. Yes. It's much more difficult. Sometimes by simulation we see only red lines and then it's problems and we think, oh, what I have to do that I have convergence. So, and you see it's much more difficult now, yes? My geometry has big deformations and it's not so easy to calculate. It needs much more time. See, it's program not finished. Now program tried to calculate 0.98. Okay, I repeat, 1 second is maximum force, 200 Newton. So, and then we see here this 200 Newton in second, and it's much more difficult. Do you see? 100 system of linear equations we calculated. Now, and it's deep. So now we found solution. So, and if you see now solution, oh, deformation is really big. Yes? Do you see? Twice more force, and we have deformation 150 millimeters without ledge deflection. Yes, one. But we have big deformation. We have to say to program, please recalculate always geometry. And if I have now ledge deflection on, then I will have not more 150 millimeters of deformation, but we will see now how much. So ledge deflection on is correct. Yes, it needs more calculation time maybe, but it's correct. So we see same story, 0.7, program tried to find solution. This is error, what I need to reach, and this is actual error. I didn't reach this error, then it's red. I tried to calculate less force. So, and then we will see what's happened. So we see red is bad, yes. Program tried to solve. It's not possible. Program will make less force. Again, red. Yes, do you see? It means I cannot solve 100 Newton or 200. Yes, I can solve maybe 1 Newton, then 2 Newton, then 3 Newton. Yes, step by step. So, okay, and we see that ledge deflection on is very important to define. So we need nonlinear effects, yes. We need R6, no. We need ledge deflection on, and then maybe we will get correct simulation, real simulation. So, but this simulation is again wrong. So we have again wrong results. It's better, but it's also not correct. This is also one point that many people forget.
Is intentionally making it wrong. We are making it correct step by step.
Okay, it's much more time. Do you see 140 system of linear equations calculated? And it goes in really small steps. See, this is our time increment. Yes, time increment. 0.3 was now we calculate with 1.8 e minus 2. Really small steps we are doing to find solutions. So, and all this knowledge we will use in 2 weeks for real simulation. We are doing one mechanical, one flow simulation, and we need to know what we have to check to switch on to do our simulation correct, and it needs a lot of time. Force convergence, and now only now I found solution after 200 system of linear equations calculated to find the solution. And now, for example, it's only 50 millimeter deformation, 3 times less, yes, with less deflection. And it's look not so bad like all the results. So, this simulation is much more better, but this simulation is also wrong. So, 600 megapascal, okay. And this is the last point for today, how we can do correct simulation. So what is wrong? Now I think it's everything good. I have non-linear material properties. I said I don't have this interpolation. I told program I have big deformations. I need to calculate it. My geometry always new. And it is wrong. What's wrong? Wrong is material properties. So this is the next point. Why my material properties are wrong? This is very simple story. This material properties, what we did, this is measurement. Yes? This is measurement. And yes, for example, if I have small deformation, then it's correct. Yes, it's my deformations like here, this point is 320. But now I have 600 or like this one. Yes, 600 megapascal. This is big deformation. And what is the difference now? The difference is what is wrong? Wrong is material properties. So the problem is, okay, if I have 400 Newton, it's again, yes, my stress, my strain, and my deformations with and without edge deflection, and then convergence. So the problem is that measurement is not real, is not what is real. So what's happened? I have my measurement. I don't have desk to show you. The problem is really simple. Bad without desk is bad to show. So the problem is my measurement. Yes, I take my part, my beam, and I pull my beam. Yes, so before it's broken. So, and what's happened in moment? If it's broken, I have my area is really small. Yes, in this moment. So, but how I do my measurement? I give, for example, 100 Newton force, and my stress is force divided area. Yes? It's really bad to show. I don't have slide. Okay, only here. Yes? My measurement is force divided my initial area. But at the moment, at the end, my area is different. My area is always different. Yes? So it means my measurement is always wrong. So, and I need to recalculate my measurement to do a stress. So, and then in a mechanical, people call it engineering stress, engineering strain. It means measurement. Yes. By measurement, I pull my part is broken. I say how much is stress. Force divide R0. R0 is my area. But in reality, my area is always smaller. Yeah? Always different. Yes. And by broken, my area really small, and my stress at break is much more high as measurement. Yes. So, and this I have two lines. One line is measurement, and what's in real? In real, it looks like this one. my stress strain diagram. Yes? So it means my stress will break much more higher in real. And this is the problem. I need to recalculate my ANSYS calculated always this true stress line. So ANSYS think that what we define, we give him true alignment. So absolute correct if we always make a calculation from engineering to true stress. But often if I have 600, it's not particularly stable. So often my parts are in this part, yes, near tensile stress. So, and I don't need, you can recalculate, but you will not see big difference. So, only if I, in this part of my line, by big deformation, I see big difference. So, but it means this is last point, what's wrong is, I need recalculation. So, and you can use my Excel file again, as an Excel file to do this recalculation. And it's same in every software. So, every software use it. You can open file, Excel file, it's called true stress. This is my recalculations from measurement to ANSYS or to real stress. So, how it works? Very easy. If you move diagram, so no, not move. You see it. Yes. You see here 3 points from diagram. Yes. I need to recalculate these 3 points to true stress, true stress. So, how it works? Very easy. I say here, okay, my engineering stress, engineering strain. I write these points. Yes. Okay, 0. Engineering strain is 0. Oh. Then right mouse button. And you can, okay, or I can write 0.00. I exclude and then you will do all your simulation absolutely correct. If you do these all steps, and then strain.
I don't remember. In the video.
And other part 308 and 75
body size.
1.
Body size, not face size. Delete it.
So and 660. So, and these are calculations. Yes, this is the calculations. Engineering measurement to real. So, real stress. So, you see stress at break by measurement was 660. Stress at break in reality 1000. So, and ANSYS use always this one. So, what we define is this one. Yes? It's easy to show difference. Normal, I have not so big deformations. For example, if I have had 0.05 deformation, then it's not so big difference, yes, between 2 points. And then many people say, oh, okay, I use this. But normally you have to use always true stress. So, okay. It means I have to define this line in ANSYS. So, but interesting is this is plastic stress, next problem, yes? The next place to make mistake, and many people make mistakes here. They think that this line is total strain, yes? But in every software, same story, I need to say separately where is plastic part, where is elastic part. So, and here is also, we define measurement is total strain, yes? Total, plastic plus elastic, yes? And ANSYS and other softwares want to see separate the plastic. So, it means what I have to do correct simulation. So, please close your simulation and open material properties. So, and now we need to define it not with bilinear kinematic coordinate. In ideal, we have to define it with multilinear kinematic coordinate. So, we delete bilinear, we will use multilinear, and the big error what people make here, megapascal changed. Yes, that they see that by measurement, if I make measurement line, then many people write here this measurement line. But measurement is for total strain. Yes, we need this recalculation always. So, and this file what I have is this recalculation. Yes, it's all what you need to define in ANSYS. You need to define this point. Yes, and year model of course. So 200,000. Okay, this point we need to define, and then we will do our simulation absolutely correct. So easy story in reality. So we say zero strain plastic strain is 318.8, and it works in every software. So this always this situation 0.4353, and stress is 1000. So, and now we define absolute correctly our line. Okay, we don't see it now so beautiful with two lines, but it's correct. And it means if I have measurement 10 points, then it's also wrong to write these 10 points in ANSYS. I need to recalculate these 10 points from here to here. Always. Yes, from engineering stress measurement to true, to what in reality. So, this is important point, and then if I do it, and then I close, and I do my simulation again, then we did everything what we need to do correctly. So, but you understand every step costs time, and then yes, it's ideal if you don't know, better to use all of this point. So, okay, and now we will see what's happened. Okay, what we need to use, everything no, non-linear effects yes, large deflection on, through a stress, through a strain. So, and this simulation will be correct. And it worked much more better. Not now, yes. Now we have problem, then red line means we are trying to calculate with less force. Yes. And then again red, again less force. And then we always hope that line goes down. Now we found solution. Let's see, and then red, green line. Yes. And we are always our hope that red line goes under blue line. If it happens, then we found solution for this point. So like this. It's interesting. Time is very quickly by simulation. So you see that 70 hours or 18 hours comes very quickly. You are watching all these diagrams, very interesting.
Forces applied for 70 hours. Yes. What will happen? Information.
So last point is material contact. Now it's database here. Here you see your more better.
It's
also. You need to see your. Oh, it's first. Maybe you delete. Yes, you don't. Structural steel. So then you can change yes, multilinear. Drag and drop, yes. Then you have to define